Hi, everybody. Thanks for joining this training session. So that's a training session that I did during the last Connect, but I haven't been able to go through all the slides. So for this time, I will probably go really quickly on what I have explained last time in order to go to the new slide. Nevertheless, don't hesitate to interrupt me if I'm going too quickly on the first slide. So last time we mainly seen all the metric and the topology description in the scheduler. And for now, for this session, I will try to explain a bit more about the load balancing, how it's working, the C groups as well, and all the new development that are ongoing. So yeah, that was the intro. We have an overview session which is available on the InnoConnect website. So I will just go through this quickly. So I will mainly discuss, present the CFS, the SCHED normal scheduler, and I will not go in detail on the other one. So topology and metrics. So yeah, the topology, as I explained last time, it's a way to describe the CPU topology from a load balancing point of view, having in mind that what we are interested in is the CPU capacity when we have asymmetry between CPU, when some CPU are sharing some core capacity, when you have some shared power domain, or when some core are sharing some resources, like accessing the DDR or sharing a large amount of cache. So yeah, and we are mainly speaking about SCHED domain and SCHED group. So SCHED domain, it's a level, and SCHED group, it's a group of CPU in this level. And then we describe the interaction between this group. So that's an example that I described last time between the SCHED domain and SCHED group. So we'll not come back on that. The architecture, yeah. We have some default topology description, but architectures can supersede this configuration to add more level if needed, or to remove some. And then, yes, we are degenerating some level. So we are building all the level by default, which means that even on a mobile system, we will create a SMT level, for example. And then we'll optimize by removing all the useless level, because we have only one CPU at SMT level. So there is no need to do any kind of load balancing. That was an example of the SCHED domain on the IK960. I will not go on that. Scalability and performance, yeah. So because the scheduler is a pass, it's a sensible pass. We are doing some per CPU SCHED domain description, so the goal is to prevent any cache contention between CPU, which might not be a problem on a mobile with 8 core, but that starts to be a problem when you have 1,000 core trying to access the same cache line simultaneously. And we also have, yes, some shortcut or some direct pointer to some level of scheduling, which makes sense, like the last level of cache, because we make the assumption that task migration between CPU that are sharing their cache is not that costly compared to moving on another socket or another node. So the metric also, I explained that. So we have the main metric, so we have this vRuntime, which is a virtual running time, which is used to decide which task will be scheduled on the CPU. It's only this that decide. I mean, each time the tick happens, we are looking for the task with the minimal vRuntime, which is a virtual runtime. So, and I will explain a bit later how it's moving on. So we have the CPU capacity and the load tracking, so per task. The goal is to ensure that we will not put some always running task on one CPU and some almost some light task on another CPU. So the vRuntime is just that we are using the task nice priority to weight the running time, the effective running time. So when you are setting the nice priority of a task, you are in fact you are describing how much share of the CPU you want to provide to this task. So the nice 0 is the default value, and then if your nice is below 0, so it's negative, it means that, so in this case, your V runtime will increase slower than reality. So which means that you will run more time on the CPU before that your V runtime reach the same level of a task with a nice priority, which is positive. So that the weight, yeah, that's something that is interesting maybe to come back on. So by default, the weight, the weight is a value associated to each nice priority, and they have been computed in such a way that when you're increasing your nice priority by one, you should have 10% more running time, and it's always a step of 10%. And I just put some example of two weights for the nice 0 and the nice 1, and I'm just explaining how it's working. So I already described this last time. You can interrupt me if you want more detail on this, if you want me to come back. So yeah, that was some example of task scheduling with different nice priority. And as you can see, so in each case, we have only one priority difference, but we can see that the scheduling pattern is not the same. And the main reason of that is the VRun time. So as I explained, your VRun time will increase faster when you have higher nice priority. And in order to the decision to switch from one task to another one is based on the VRun time value, and this happens on every tick. So in the default case of nice 0 and nice 1, we run several ticks before switching, and when we are increasing the nice priority, the VRun time will increase faster. So the switch between the two tasks will happen more often. But at the end, you will have the same amount of running time. It's just a matter that in some cases we are gathering several ticks, whereas otherwise we are just switching almost every tick. Do I need to come back on this, or it was okay? About the skate period and the skate slides. So the skate periods, it computes the theoretical time window during which all the tasks should be scheduled. And then we have the skate slide, which is the theoretical slice of time for each task. I say theoretical because we are not really trying to switch the task when the time is over. We are just waiting for the tick to make the decision, just to be efficient, just because otherwise you might schedule a new task every millisecond, which can be a kind of waste of time and throughput. Yeah, another thing is so the VRun time is local to the CPU. So we have per CPU VRun time, and when a task migrates, we need to normalize the task. So we need to remove, what we are doing mainly is that we are removing the mean value, we are migrating, and then we are adding the mean VRun time on the new CPU, just to put back this task compared to the other one. And the main reason for that is to not provide too much runtime. And so this is an example of two tasks with the same nice priority, but they have some different running and sleep period. And without this normalization, the task B might run 400 milliseconds in one shot because it will sleep quite a long time. And during this time, the task A will continue to run. So it will increase its VRun time, which means that when the task B will wake up, the difference will be quite huge. But that doesn't mean that the task B should run all this difference, because it was sleeping, so it doesn't need this amount of time. So that's why we are normalizing, to make sure that we'll keep some fairness. I think I have already spoke about that. It's about when we are denormalizing the vRuntime and where we put the task. I mean, it's really that when you have a task that is attached to a CPU, you know what is the minimal vRuntime on the CPU at that point. And the goal is to place the task so it will be able to get some runtime quite soon, but without starving the other tasks which are already there. CPU capacity, I have already described that last time, so I will not comment on that too much. It's just describing the compute capacity. That's just an absolute value. That's a relative value, sorry. So it's only meaningful compared to another CPU. Parent TTL tracking, I also mentioned that. Can come back that a bit. The goal is to track the activity of a task. And so we are tracking activity of each CFS task, each CFS run queue, which means that even if you have cgroup and several levels of CFS run queue, you will track everything. So we are tracking the utilization, which is the running time, the load, which is the runnable time with the priority of the task, the runnable load, which is the time when you are runnable. I will not come back on that much, unless you need more detail. But I already explained that last time. And the cgroup, that's the new part. So in the scheduler, we can have hierarchy of a run queue. We don't have only one run queue. We can have, I would say, how many as we want. We can create some hierarchy to say that we have a main root CFS run queue, and then we have a child on which some tasks will run. We can have another child, and we can have some such. That's typically what we call the cgroup. So that can be used mainly to, that's useful when you want to, for example, you have a user which will have X number of tasks, and you don't want him to use all the CPU running time compared to another user. So the goal is that from a system point of view, this user, whatever the number of tasks, should have the same amount of time than another user, even if the other user has only one task. So for this case, we are creating two groups, TG1 and TG2. And we can set the priority. So these tasks are seen as a scheduling entity at the parent level. And then we will, yeah?
What does C stand for?
Control group. So yeah, maybe I should have mentioned that. So yeah, we can share a nice priority. So that's what I was explaining before. So making sure that all the tasks belonging to a group, or the typical example is that to a user, will share the weight all over the system. So you can make some kind of a CPU bandwidth allocation between group of a task. So we also have the CPU affinity, so you can you can change the CPU mask of a group of tasks, especially when you want to partition your system. And you can also do some CFS bandwidth. And I think I have more detail on that. It's just that you can make sure that you will not run more than an amount of time for each source. You set a running time, and a maximum running time, and a period. But yeah, the main things to understand is that, yes, we have this tree and this topology that is describing, and for each group, each group, it's a single and autonomous run queue. And we will go through this group when we want to select the task. So the scale entity. A run queue, in fact, in order to be able to have this cgroup topology, a run queue is scheduling a scale entity. Everything is about scale entity. It's a scheduling entity. And at the parent level, we don't know exactly what a scale entity. The scale entity can be a task, or that can be another run queue. And we are just iterating each level like that. So at the root level, for example, we will select a scale entity. If it's a task, we schedule the task. If it's a run queue, we are going in this run queue and select the scale entity, the one with the minimum runtime, and so on up to the last level. Yeah, and this is per CPU. That's another thing. We don't have any, so this example will be duplicated for each CPU. So you can see how many run queue we can have to manage on some system. I don't know, on Android, I think that we have at least 1 or 2 levels of cgroup on 8 core. So you can easily have maybe 20 or a bit more run queue to manage. And the goal is to balance the task on all this, in all this run queue. So one type of cgroup, which it's about sharing your priority between all the tasks in this group. And how do we ensure the fairness between this group? So we have a nice priority, which now apply not on one task, but on a group of tasks. And this task can run on different CPU, so which means on different run queue. And in this case, so yeah, I have put this example. Yeah. So I have this, in this example, I'm starting with 2 groups, and I have only 1 task in each group. So you can see that we have the same amount of running time for each task, so for each C group. And then I'm starting 2 tasks in one of the group, which means that I have one group now with one task, and another group with 3 tasks running on 3 different CPU. But I must ensure the fairness. So I must ensure that the group with only 1 task will have the same amount of running time than the group with the 3 tasks. So in this case, we are splitting the nice priority, what we call the share, between all the run queue. So each run queue will have 1/3 of a normal priority. And that's why, I think it's 1. You have 2 running tick for the C group with the 3 tasks, and 5 or 6 that depend tick for the group with only 1 task, which means that we are ensuring that only 1/3 will be used by the group. So that's how we are working, and that's how this is working. And the main difficulty is how to share the weight between this group. Why that should be 1/3? So in this case, it's quite simple because we have 3 tasks on 3 different CPU. 1/3 is quite easy. The difficulty comes when you have 100 of tasks with different priority in the same C group. So how do we update, in this case, the load and the share of a C group? So we split as I explained, we split the weight between the scale entity of the task group, so on each CPU. And based on that, the load will be impacted. So this chart shows the load average of each CPU, of each run queue of a C group. So when you have only 1 task on 1 CPU, the load of this task will be the maximum value, 1024. But when there are other tasks that are running on other CPU from the same C group, in this case, we are sharing the weight, we are sharing the priority, and the load is divided as well. So which means that at the end, when we have 3 tasks, we can see that, we can probably not see, but both are going down. So at the end, the 3 load values are the same. It's 1/3. And so in order to maintain this load, because everything is moving all around, the number of tasks that are runnable when you are migrating tasks, so we are updating that value periodically. So we are doing that periodically and not at every task migration because of scalability. Otherwise, that will take too much time. So we are doing that from periodically, something like every tick, in order to be scalable. And we are calling this function update CFS group. That's where we are resplitting, we are distributing the weight between all the C group, between all the run queue at the C group level. So when a task migrates, we have to update all the metrics of the CFS system, and we have to update the share, as I explained. So regarding the utilization, the migration is quite straightforward because just a one-one movement. I mean, if a task that was running half of the time migrate on another CPU, the utilization will be the same. That will fully migrate. I mean, it's not divided. Whatever the number of level, it's really the running time that we are migrating. For the load, it's a bit more difficult, and we are more estimating this value than trying to get the correct value directly. And then we will just let the system to converge to the right value, mainly because the load of a task is made of its waiting time, its running time, and its weight. So when a task migrates, we can't really estimate what will be its waiting time in the new run queue. And even on the previous CPU, on the previous run queue, we don't know how the waiting time of other tasks will be impacted. That really depends if they're waking up at the same time or not. So we are just trying to estimate that to something not that bad and not that wrong with simple rules. Oh. No, it's not the right one. That's not the right one. It's probably the previous one. Okay, so I will continue. So that's for the CFS load. Now we have, if we come back to the C group. So there is a new C group that have been merged just now, which is called the UClamp control group. So the plan of this group is that, so we have this load tracking mechanism where we are tracking the run time and the runnable time of each task. But sometimes it's not enough to have the right view or to get the right constraint for a task. I mean, you can be a small task, so you're waking up and running some short time, so your utilization will be low. But you want to run quickly because you're on the display pipeline, for example. So even if your utilization is low, you want to use the highest frequency. And at the opposite, you can be a background task which are running for thousands of milliseconds, but you don't really care of the amount of time that will be used to run that. Just a background activity. And you don't want to run all the CPU at the highest frequency for this. You prefer to spend twice, 10 more time, but at a lower frequency and save the battery. So in this case, you can use this uclamp cgroup, where for a group of CPU, you can cap the mean and the max utilization value that will be seen by the scheduler and the CPU frac system, which means that you can say even if whatever the utilization of this task, the scheduler will know that the minimum utilization value will be this value, and you will have to adjust when selecting a CPU if you have big and little CPU, or maybe this is not yet merged, or when selecting a frequency. And you can also set a max utilization value that will be seen by the scheduler. So even if you are an always running task, the scheduler will think that the needed utilization is low, and you will select the lowest frequency. So this is used by Android, for example, in their foreground, background, top app. I think now that there is this background cgroup as well. So they are using this to make sure that the background cgroup will use lowest frequency and that the top app cgroup will ensure minimum frequency to be responsive. Do you have any question on one topic, on one specific part, before I'm making that more complex? Yeah.
I have one question about the NICE.
Yeah.
If you come back.
This?
Yes, this one. So, referring to this diagram, this figure,
yeah.
That means if we have, for example, interactive tasks, we want them to be switched quickly.
Yeah.
We can have the same priority between them, but increase the priority to a nice 18 versus nice 19.
Yeah.
So they switch quickly. Is that the point?
Yes,
So
but you will have less time compared to. So the point is that if you put this nice 18 with the nice 0, you will have, I'm not sure to do the right computation, but you will have probably only 10% of running time because your nice priorities, you're nice to the other task. And what happened, in fact, this is mainly because in the scheduler, so we are updating the VRun time, and we have a function to know if we should preempt the current running task to schedule another task. And this is based on the VRun time. So we ensure a minimum running time of a task before being preempted by another one. So, and in fact, it's a minimum VRun time. So with nice 0 and 1, your VRun time will increase slower, which means that you will have more real running time before being preemptible.
Yeah.
Whereas at this lower level, your VRun time is increasing faster, and you will be preempted almost immediately.
Yeah, but in case of interactive tasks, maybe we want to have, if we have two tasks, and we have both of them, we want them to interactive. The setup with the nice 18 and 19 is more interesting than the setup with nice 0 and 1. So that's just my question. Fine.
Maybe not. So we probably want the interactive task to be of a higher priority. So the deal is that because it is an interactive task, it should not run for longer period of time.
Yeah.
It should just run and it should.
Exactly.
Okay.
Because of that, it should have lower nice value, so it gets more period of time to run. So as soon as it is ready, it gets a chance to run, but it runs for like microseconds and then gone again. So you're not required to interrupt interactive task at all. It should give the CPU away anyway.
Okay. Okay.
Yeah, because, I mean, if you run, the throughput at this value will be lower than there because you are doing most task switching.
If you make it a big nice value, you will see the lag in the mouse cursor. You will see a big lag.
Okay.
Other questions?
I have one question.
Yeah.
So for the C group slide, where you were showing 3 tasks in a C group and 1 in the another one.
This one?
Yeah, so what I thought earlier was that if there is 1 task in one C group and 3 in the other one, eventually they will have the same amount of time they will run. 3 versus 1. So the first C group with 1 task will run for 5 milliseconds, and the other C group with 3 tasks will also run for 5 milliseconds only. But that doesn't look to be the case here. It is only about weight rather than how much time they run.
So yeah, so the point is that for these 2 tasks, I mean, they have all this running time because there is nothing else to run. That's the point. I mean, we'll not, the CFS bandwidth C group, with this control group, you will throttle the task. But with the share, the default one, I mean, if there is some compute capacity available, some spare capacity available, you will use it. So that's why.
Right, but so from this diagram, it still doesn't look fair because the C group, which has just 1 task, it runs thrice the amount of a task of only one of the tasks of the other C group.
So
While the other, so if you see the first for CPU 2, so 1 task of a C group which has 3 tasks, it runs for X amount of time, and the other task from a C group which has just 1 task, it runs for 3x amount of time.
Yes.
But if you see the other 2 tasks, they run forever. Right. So eventually, it is not fair. So
between tasks, you mean
between
so
the groups?
In the C group, yeah, I agree. In the C group, between this task and this, it's not fair.
Even the other way around, between C groups as well. So if you sum up the yellow line, the green line, and the gray line, they will be much higher than the red line.
Yeah, because because the C group with only 1 task doesn't need more compute capacity.
What if it does?
Oh, if it does, so yeah, maybe I have pinned the task just to show the difference. But I mean, if some task from the red C group wake up on the other CPU, they will preempt that in the same way.
So okay, to make it simple, if we have just 1 CPU here, then.
So if we have only 1 CPU, let's say that these 2 tasks, we put everything on the same.
Right.
So in this case, we should have, so these 3 tasks will have the same amount. The sum of these 3 tasks will be the same of only of all of the other tasks.
Okay, then it is fair enough.
Yeah.
Is it correct to say that this share system only is enforced when there is contention for the resource, right? If there is plenty of resource, we don't care. We give everybody what they want, right?
Yes.
Yeah.
Yeah, unlike the CFS bandwidth, so yeah, the slide are not there, but with the CFS bandwidth control group, you're specifying a runtime, a period and a runtime, and if the task of a C group consume more than the runtime in the period, they will be throttled. And you will have to wait for the end of the period before restarting them. Other question? So another activity that's happening on the kernel right now is flattening the run queue. So I have described this where we have this hierarchy of run queue. And what's happened is that when you want to schedule a task, you start at the root. You select the sched entity, the one with the lowest vRun time. And if it's a task, it's finished. Otherwise, you take the child run queue, and you select the sched entity. And you go through all this tree, which is really time consuming. I mean, it's the overhead can be quite significant when you have 1, 2, 3, or 4 level of C groups. So there is some ongoing discussion to flatten that, so all the tasks will be enqueued at the root at the root run queue, and we will only maintain a hierarchy for the run queue topology and for updating the share between the tasks. So it's ongoing. It's not yet there because we have a lot. There is the main problem. It's about when a task wake up and how you place this task compared to the other task of other groups. Right now, what's happened is that when a task wake up, the task is enqueued in its run queue. So the runtime is normalized compared to this run queue. If you flatten everything, when you are enqueuing a task, the runtime must be set compared to all the other tasks. And you can be in a situation where if you have a lot of tasks of a group that are enqueued at the same time, they can just be set to a value that will preempt all the tasks of another CPU. So we expect that to be happen, but yeah, there are still a lot of change to be done on this. But yeah, we can expect some number of percentage of improvement in the overhead. Yeah, I don't. In this slide, we don't have the load balance. So when you have a number of tasks, you have to balance the tasks between the different CPU or between the different cgroup in the CPU. And so for that, we are using the load because the load reflects the amount of runnable tasks or the amount of tasks on each CPU. And the goal is to be fair. So as I explained, so in this case, if we took this example, between the yellow, the green, and the blue, we are not fair. I mean, they don't have all the same amount of running time. So we are doing some load balance. The load balance, it's only about pooling tasks. So periodically, a CPU will look at all the other CPU and see if it should pool a task. We are never pushing tasks. We are only pooling tasks. And we have three kinds of load balance, which is linked to the state of the CPU. So the first one is what we call the busy periodic load balance. So when the CPU is busy, periodically we look if we should pull tasks from a busiest CPU, for example, or CPU with more tasks. We have the idle load balance. So when a CPU is idle, from time to time, we are checking if we should not pull some tasks from another CPU. So in this situation, we are not waking up all the CPU, but we are waking up one CPU that will run the load balance for all the idle CPU that improve the power consumption. And we have the newly idle load balance. So when the CPU become idle, we look if we are checking if there is an opportunity to pull a waiting task on another CPU. And this is done for each scheduling level. I don't know if you remember there. So we are doing this load balance at each level. And in order to be scalable, we are not using the same period interval between each level because of the cost. I mean, migrating tasks between two CPU, which are sharing almost everything, it's not really costly. We can do that quite often to make sure that everything is balanced. But at a NUMA level, before migrating a task, you must be sure that it works. And because of the number of CPU involved there, you can't do that every 10 milliseconds, for example. So we are running the load balance at each level periodically, quite more often at this level and from time to time at this level. And for each C group. No, not for each C group, sorry, I'm saying. And yeah, one time per CPU. So in the mainline kernel, everything is based on the load, as I explained, and there are some ongoing activity to change that in order to have a better classification of the CPU. So the goal to group of CPU is mean that before doing some load balance, you have to look at the state of each group of CPU to understand if the group of CPU has some spare capacity and can pull more tasks, or is fully busy, so there is no spare cycle. But maybe another CPU, the group of CPU is overloaded, and you will have to pull some tasks. So you can classify the group of CPU as overloaded. So there is too much task, not enough compute capacity for all the tasks. And we have few other specific situations, which are when we have a misfit task for big little system. So when a big task is running on a little core, we are able to tag this task to say that it's misfit with the CPU. It needs a bigger CPU, and we should migrate that. Whatever the situation, we will rebalance things after, but at least these tasks must run on a big CPU. We have something similar for Intel platform, which is called asymmetric packing. And we have the imbalance state. It's when you start to set some CPU affinity on task, the load balance becomes even more complex, because when you are evaluating the load on each group of CPU, part of this load can be moved. So that makes the balancing even more difficult. And in some situation, you can have the situation where the only task that is runnable and waiting can't be moved on an idle CPU. So you have a task which is pinned to a CPU and can't be moved on the idle CPU, whereas probably some other tasks which are running, and that's also something, should be moved. So yeah, we are only moving some waiting task and never the running task. A task that is running can be migrated. So when we want to migrate a running task, we schedule a stop class, so a higher priority task that will remove the task from the running state so we can pull that task. So the imbalance case is when we have an imbalance, but we can't migrate any waiting task, so we are just going to try to pull one task, whatever the task, and then we'll figure out how to solve this imbalance at the next round. What else I haven't mentioned? Yeah.
How would the scheduler know that a particular task is not moving up from this CPU and it
Oh yeah, the mic.
How would a scheduler know whether a particular task needs to be moved, like it's not on the right CPU? How is that information saved in the scheduler?
What do you mean by not?
Like you were saying, you would migrate. Like if you think that something is on a slower CPU,
Yeah.
you're going to migrate. But how does the scheduler have that information as to how long this task will be running? What would it be doing in the future? How would it make that decision?
So for each task, we have the utilization metric. And this utilization, the longer you're running, the higher the value is. And this value can be above the compute capacity of the local CPU. In this case, it means that the task would run more than what is available on the CPU. So we can tag this task as misfit, and that's a way to know that we have to migrate. We can use the uclump cgroup, so the user space can say, okay, this task, you will consider that the mean utilization of this task is a high value. So this task must run on a big CPU, for example, or at higher frequency.
But aren't there other metrics that give input to the scheduler? Say, for example, I see NUMA nodes there on your topology. So things like, where the pages that are used by that process are. That's one kind of input.
Yeah, that's another thing. But the NUMA scheduling is happening at another level, and in this case, we are. So the metric, we are computing the number of, that depend of the location of the page, memory page compared to the location of the CPU. We are trying to put everything on the same node whenever possible.
Actually, there are two questions. How do you deal with the tasks which react to the asynchronous sort of user input or asynchronous access patterns? So you may be in a situation when tasks just reacting to what's happening around, and the schedule will reschedule them in and out of the different cores, will try to merge them and move them in and out, but we will have overhead of the scheduler on one hand. On the other hand, it will not really do much good to the system.
So for this interactive tasks, which are usually they are short running tasks, the uclamp is one solution for such kind of task, because you can set some minimum capacity or some minimum utilization for them. So you will ensure to run on a large enough CPU, for example, or at high frequency. And then regarding the spread on the CPU, that really depends on how much other tasks are running. So when a task, wake up, the task wake up on the CPU where the task, wake up on the local CPU. And then we have to select on which CPU we want to put the task. So usually we have several paths in this wake up. One is the simplest one, where we are comparing the previous CPU on which it was running compared to the local one. Which one is the best? So we are trying to look for an idle CPU.
So you do have mechanism to avoid the ping pong of the task in between multiple CPUs. So you do remember a bit of history of what happened to that task in,
So we have the previous CPU mainly. That's the main things that we have. Because we are trying to stay local unless the previous. So that's where it's become difficult, because we have to find a trade-off between cache hotness, and that's another thing that I haven't described. That we have some buddy tasks, so we can try to. The goal is we try to keep the cache hot with task. So we'll try to schedule the task on the previous CPU until a number of time, but also at some point, if the task always wake up on the same CPU, that may mean that the hierarchy or the task that wake up this is there. And if they are sharing some data, that's an opportunity to stay there and take advantage of the cache hotness as well. And we don't have any. This part still have a huge number of heuristics where we are trying to detect the wiki mechanism, where if you have one task, so when two tasks are waking up each other, we are trying to detect that and keep them on the same CPU. And if one task is waking up a lot of tasks, at some point we don't want to keep the other task on the same CPU, because they will just wait before running. In this case, we want to spread that in the same on all the CPU at the same cache level.
And one more question is, how do you deal with the busy polling? So there are tasks, and again, when you try to poll very fast hardware, so busy polling pretty much the only option, right? And you may need to poll different things, so you may have multiple busy polling tasks, and kind of how that plays with.
For us, busy polling tasks are just task computing something. We don't have any, from a scheduler point of view, we don't make any difference.
It's just runtime.
Yeah.
Okay.
Whether you do that or you do something else, it's the same thing.
We have one information for task waiting for I/O. We have the I/O schedule waiting task, and we have the I/O boost at the CPU thread level. So to make sure, for example, because you can be in the situation where if your task is doing a lot of I/O transfer, it can wait for the I/O to terminate. So this waiting time will be seen as a sleep time. So you can be in a situation where your task, the utilization of a task is not that huge, because it's spending most of the time waiting for the hardware or the I/O. But you still need some high frequency, because the bottleneck is you filling the I/O with the next data to transfer to read. So we have this I/O boost mechanism. I think we are done. Maybe one last. I don't know if there is another meeting after, but we ran out of time. One last question.
You mentioned that we are not going to look at load for load balancing.
Oh yeah, I haven't finished that. So yeah, so right now it's only about load. In the current, what is merged in mainline right now, it's only about load. We are reworking the load balance. So I have explained this classification between group with spare capacity, group fully busy, group overloaded, and so on. And based on that, then we are not only looking at load, but we can decide to move tasks or to move some utilization or to move some number of tasks. That's a new mechanism that we are trying to put in place. Right now, because the load is not always the best way to describe the imbalance. It's a good way to describe the imbalance when the system is overloaded, because you have to share the running time. But when your system is not overloaded, what you want to do is mainly to fill the idle CPU. So that's a new mechanism now where, depending of the state of the scale group, you can decide to migrate some task, migrate some utilization, or migrate some load.
So it's purely based on utilization. You're not going to look at load at all.
If the group are overloaded, in this case, we are looking at the load to ensure the fairness. But if the group are not overloaded, you will just try to fill this spare capacity. Yeah, I think we have done. Thank you.